Next topic is losses in induction machine. So till now we completed construction, working, and slip formulas and rotor parameters and starting and running condition. After that, there is a power flow in a induction machine. After power flow, there is a torque. Torques are maximum torque, full load torque, and starting torque. So these torque equations are derived. In that maximum torque, Tm equal to E2 square by 2x2. Maximum torque does not depend upon the rotor resistance. And when electromagnetic torque is equal to load torque, then machine is running at a stable condition. So remember that in a torque slip characteristics at starting, T is inversely proportional to slip. So torque is inversely proportional to slip. So the torque slip characteristics are rectangular hyperbola. When it is under running condition, torque slip characteristics are linear, T proportional to S. Now the copper losses. So now the topic is losses. We know that losses are two types. One is the iron losses, and the iron loss also called constant losses. And second type is the variable losses. So in the constant losses, there is a hysteresis and eddy current losses. Hysteresis losses, which is because of magnetic reversal of stator core or rotor core, and eddy current losses is because of when the cores are cutting by the fluxes, then EMF induced in the cores, that may be stator core if it is an induction machine. So the induction machine stator core cut by the fluxes, then EMF induced in the stator core. So that EMF creates the circulating current in the stator core. That circulating current is called the eddy current losses, and the power wastage in the stator core is called the eddy current losses. So eddy currents are and hysteresis loss are both are exist in the stator core only, and this both are constant. It is independent on load. But this hysteresis losses and eddy current losses both depends upon the frequency. It is an induction machine. Hysteresis and eddy current losses only present in the stator, but not in the rotor. Only present in the stator, not in the rotor. Because in the rotor frequency under running condition is very less. That is rotor frequency far equal to slip times of stator frequency. The rotor frequencies, it is in the order of 1 to 3 Hz. One to 3 Hz. So rotor frequency is very less. So iron and hysteresis loss are very less. In the three-phase induction machine, hysteresis and eddy current loss are cancelled in rotor core, but there is exist in the stator because stator frequency is equal to supply frequency. is equal to supply frequency. Copper losses are there in the rotor. So copper loss is very dominant in the rotor. Copper loss exists in the stator and in rotor, but iron loss are more in stator and less in the rotor. Eddy current losses B square F square. Eddy current loss is proportional to frequency. Hysteresis loss proportional to the frequency. So the less frequency in the rotor, negligible eddy current and hysteresis loss in the rotor. In place of B, substitute the V by F, because B maximum equal to V by F. From the equation, transformer equation, E equal to 4.44 F pi. In place of pi, replace pi with BA. B is the flux density and A is the area. So B equal to B proportional to E by F. B proportional to, from that equation all terms are constant, E and F. E equal to F B. So B equal to E by F. E also called V. B proportional to V by F. So then we get answer P proportional to V square. Mechanical losses are friction losses, bearing friction losses, that is brush bearing friction losses, windage losses. Bearing friction losses are there in both the machine, squirrel cage and slip ring induction machine. Brush losses are there only in the slip ring induction machine. Brush losses are there only in the slip ring induction machine. Windage losses are proportional to NQ. So to find these losses, we go for two tests. One is a no load test and another one is a block rotor test. So this no load test is done between when slips are between 0 to 1. To find the center branch parameters R0 and X0, and it is to find the constant losses of induction machine. No load test is to find the center branch parameters R0, X0, and it is to find the constant losses of induction machine. Rated voltage and rated frequency. So this test is done at a rated voltage and rated frequency conditions. Rated voltage and rated frequency conditions. So keep V by F constant. Increase the voltage and frequency. So that maintain the V maximum constant, and it is increasing. See, this is the diagram of the laboratory. So there is a 2 watt meter method is used here. So usually 1 watt meter method is enough, but it is not a balanced condition. 1 watt meter method is useful when it is balanced condition. Load is balanced condition, but it is not a balanced. We can't maintain the balance in the three-phase induction machine. So there is a 2 watt meter method is better. 2 watt meter, current coil and pressure coils are connected. Current coil is connected to ammeter and pressure coil is connected across the voltmeter. This wattmeter reads the losses. If power supply is balanced, then 1 watt meter is sufficient. Otherwise, 2 watt meter is required. Okay, if power supply is balanced, then 1 watt meter is required. Otherwise, 2 watt meter is required. Wattmeter reading based on the power factor. Relation between wattmeters. If wattmeter 1 and wattmeter 2 reads equal, then there is a unity power factor. If wattmeter 1 reads double than wattmeter 2, then power factor is 0.866. If one wattmeter is reading 0 and another wattmeter is showing the total three-phase power, then power factor is 0.5. If one wattmeter is showing positive value and another is showing negative value, then power factor is 0. When wattmeter reading negative value, then reverse the pressure coil or current coil terminals. Reverse the pressure coil or current coil terminals. At no load, power factor is very less. Under no load current condition, magnetizing current is very less. So we know that cos pi, that is power factor cos pi proportional to I mu by I naught. From that, I mu is very less because under no load condition, magnetizing current is less. When I mu is less, then power factor also very less. So the no load test is, it is to find the center branch parameters. So this is the equivalent of center branch. IW is the working component. IMU is the magnetizing current. Here IW equal to I naught cos phi naught. IMU equal to I naught sin phi naught. IW, IMU, I naught. See the vector diagram and draw the vector diagram. IW, IMU lags with 90 degrees. I naught is a no load current. WI equal to W1 plus W2. WI is the iron losses. To separate iron loss and mechanical losses, maintain frequency constant and reduce the voltage. So the wattmeter 1 wattmeter 2 values are equal to iron losses. Block rotor test. So this is the also called full load test. So in the block rotor test, rotor is not rotating. The power supply is given, three-phase power supply is given, everything, but the rotor is stop rotating by springs. By adjusting the springs, rotor rotation must be zero. When rotor rotation is zero and three-phase supply is given, then the machine is said to be operating under block rotor condition or maximum load condition. To find the full load copper losses, so this test, block rotor test, is to find the copper losses in execution. So a reduced voltage is given, reduced flux density, by the block rotor test, reduced voltage, reduced flux density, current drawn is more. When the voltages are very less, then currents are more in block rotor condition. So the when currents are more in the block rotor machine, copper loss are more and iron loss are here. Starter iron losses. Here iron loss are less because of voltage is less. Voltage is less and flux density also less. So the available flux in the machine is very less. So when flux and voltage flux densities are very less, iron loss are very less. So in black rotor test only the copper loss are existing. Only copper loss are existing. So the copper loss is equal to wattmeter reading 1 plus wattmeter reading 2. Mechanical loss are more in a slip ring induction machine because air gap is increasing, magnetizing current also increasing. Cos pi is decreasing. TST is decreasing. Windage losses more for the slip ring induction machine because air gap is more for slip ring induction machine. When air gaps are more, windage loss are more. During no load test, induction machine motor draws the power for core loss and windage losses and friction losses. So these are the losses and tests which to conduct to find the losses in the machine. To find iron losses, we go for no load test. Under no load condition, the slips are between 0 to 1, and block rotor condition, slips are between at 1 only because n are equal to 0. So by the no load test, we can calculate the shunt branch parameters also, and by the block rotor test, we calculate the copper losses and series branch parameters like R02 and X02. It is similar to the transformer SC test and OC test. No load test in induction machine is equal to open test OC test in a transformer, and block rotor test in induction machine is similar to the short circuit test is equal to the short circuit test. So in block rotor test condition, W1, W2, this both wattmeter readings are the equal to copper loss. Windage loss are more in a spring induction machine because the area is more. Next topic is speed control methods of induction machine. Speeds of induction machine can be controlled from the stator side and the rotor side. Rotor speed nr equal to ns into 1 minus s. Ns equal to 120 f by p. Stator voltage control method. For stator side there is a stator voltage control method, and stator frequency control method, and pole changing method. So stator voltage control method and stator frequency control method for both machines. that is squirrel cage and slip ring induction machine. Pole changing method is only for squirrel cage induction machine and is not for slip ring induction machine. Because in a squirrel cage induction machine, pole changes, rotor pole changes by automatically by the induction process, or we can say squirrel cage induction machine poles are induced poles, while slip ring induction machine poles are manual change poles. It is not induced poles. Our rotor side control. The rotor side control can be possible by rotor resistance and EMF injection method and cascade method. But rotor side method is suitable only for slip ring induction machine. It is not for squirrel cage induction machine. So right, starter side controls, starter voltage control, starter frequency control, and pole changing method. So pole changing method is not suitable for the slip ring induction machine. Rotor side controls are rotor resistance control method, EMF injection method, and cascade control method. So the rotor resistance, EMF injection, cascade methods are only suitable for the slip ring induction machine. Speeds, torque, power characteristics. See that speed is taken as reference. If speeds are increasing, then powers are increases up to rated value. When we get a rated value, rated power value in the machine, even speeds are increasing, powers are constant. Because if powers are increasing in the machine above rated value, the machine will burn. So power is constant after rated value. And the torques are increasing from 0 to when speeds are 0 to higher values. When powers are increasing, torque maintain constant, and when powers are constant, torque is variable. So as we know the formula P equal to T omega, from that equation P equal to T omega, omega equal to P by T, omega equal to P by T. When powers are variable, torque is constant, and torque is variable, power is constant. So first one is the starter voltage control method. In a starter voltage control method, you know the torque formula, torque proportional to SE2 square by R2 square plus X2 square. So from the torque proportional to voltage, torque proportional to SV1 square, actually torque proportional to SE2 square, E2 and V1 are proportional, so torque proportional to SV1 square, T by S proportional to V1 square. When the voltages are decreasing from the rated value, the rotor resistance. So to maintain torque constant, slips are increasing. See in the equation, T by S proportional to V1 square. When V1 value is decreasing from rated voltage, V1 value is decreasing from rated voltage. To maintain torque constant, slips are increasing. Torque constant is increasing. When slips are increasing, in the above equation, rotor speed n are equal to ns 1 minus s. So ns is the rotor starter flux speed and s is the slip. When the slips are increasing, when voltages are decreasing, slips are increasing. When slips are increasing, rotor speeds are decreasing. NR is reducing. Voltage must not increase above rated value. So voltage must be decreased. So voltage is reduced, then speeds are reduced. When machine is running at zero speed, the voltage is zero. If voltage is increased, the speeds, rotor speeds are increased. The voltage is increased up to rated value only. Okay. Speed, voltage characteristics are linear. This is the problem. A 3-phase 4-pole 50 Hz induction machine, and it is connected to a 400 volts running at 1450 rpm. If supply voltage is reduced to half, then speed of induction machine. So actually 400 volts is there. From 400 volts is operating, then speed is 1450 rpm. If voltage is reduced to 200, half means 200, then speed of induction machine. So when you should calculate the two slips here, because here voltage is reduced from 400 to 200, the slips also increases. See that S1 equal to 1500, 1500 because of NS value is 1500 because of 4 poles. 1500 minus 1450 by 1500, so we get a 0 0.03 slip values. If torque is constant in the previous equation, T equal to SV1 square, T equal to SV1 square. The slip and voltage are constant. Slip and voltage are constant. Maintain torque constant. Slip V1 square is equal to S2 V2 square. So we want S2 value. V1 value is 400 volts and V2 value is 200 volts. So S2 value is equal to 0.12. 0.12. NR equal to NS 1 minus S. NS equal to 1500. S equal to 0.12. NR equal to 1320.